Now that we've talked a bit about FutureTask and described essentially its structure and functionality, we described its key methods, we're going to take a shot at explaining an interesting context in which you can use FutureTask. And this should look a bit familiar because we've talked about this before, but we haven't talked about it in the context of FutureTask. So what we're going to do is we're going to use it to implement a Memoizer. And if you recall, a Memoizer is a cool data structure that can be used to cache the results of long-running functions and then return those cache results subsequently when someone wants to get those results, so they don't have to do the long-running computation over again. We typically use memoization as an optimization technique to speed up programs that may end up doing a lot of duplicate computations, so it's better to look them up than to recompute them. Here's just a quick recap of what a Memoizer does. We've gone over this before, but I'll just recap it so you don't have to go back and watch old videos. So imagine we have a method called, say, compute if absent, and that method is going to take a key and it's going to take a function where the function is a Java 8-like function. If the key doesn't exist in the cache, then you apply the function that's associated with the key, and then you store the resulting value in the Memoizer with the key as basically the key that will be used to look up the value later. And then you return the value that's associated with that key. So that's what happens if you look something up where the key is not yet in the map or in the Memoizer with the value associated with it. If somebody comes along again and gives the same key, then rather than go through the process of doing this long-running computation, it simply returns the value that's been stored inside the Memoizer somewhere. So it's basically just a memoizing cache. That's the best way to think about this, with the main difference being that there's a function that can be used to perform the computation the first time in. So basically, if you take a more detailed look at this, you can see that Memoizer here has an interface and it's got an apply method, and that's where the bulk of the heavy lifting is going to be done. And you can see that what we do here is we implement the Memoizer by using the function interface. This would be a Java 8-like interface. Of course, if you don't have Java 8, you just have to define your own version of function to work the same way. You could certainly do that yourself. The great thing with Java 8 is that now comes built in to the libraries that come along with Java for Java 8 and beyond. The particular implementation we're about to look at is based on some discussions and an example that's in the classic book, Java Concurrency in Practice by Brian Getz and his colleagues, which includes Doug Lee, who we've talked about before. And it's a great book. It's a little bit dated at this point because it really applies to kind of Java 5 era mechanisms, but it's still got some great discussions and it's very well written. And this particular example is a lot of fun. So the way this works is if, as I said before, if the value has already been computed, when we call apply, it just gets returned rather than going ahead and running the function to compute it. And one of the reasons why we have Memoizer implement function is we can use function, we can use a Memoizer anywhere where a function is expected, or we can just go ahead and pass in a function. So if you don't want to do the caching feature, then you can just pass in a regular old function and it'll get called every time. But if you want to use the Memoizer, you can transparently add the memoization mechanism to any interfaces or any APIs that expect to get a function. The way we're going to implement our particular Memoizer is we're going to use concurrent hash map. And the intent of this is to minimize synchronization overhead. We've talked about this many times before. The reason why I want to do this is that there's different lock guards for each hash table bin in the hash table. So if you've got, n entries in your hash table, then there'll be a different synchronizer, basically a compare and swap operation for each of those things. And as a result, contention is very, very low because we're using lots of different locks. In contrast, if we had a synchronized map, then we'd end up with a single synchronizer being used there, just good old synchronized statement. And therefore, there's going to be a heck of a lot more contention because everybody has to go through that one synchronizer as opposed to kind of spreading it out by using a different synchronizer for each bin in the map. This example uses a compute value method where it's going to be based on the future task to ensure that the function runs only when the key is first added to the cache. And this is going to take advantage of some really cool semantics of FutureTask in order to make all this behave properly. So why is this important? The reason this is important is if you have multiple threads that are all concurrently calling compute value on the same Memoizer at the same time with the same key, and that key doesn't yet exist in the map, then only one of those threads will actually do the computation, and all the other ones will simply be beneficiaries of the results of that computation. So we don't do any extra work here. We do no extra work than necessary in order to be able to get the semantics that we want here, which is basically an atomic check then act style mechanism. So that's the end of the overview of how we're going to use FutureTask to implement the Memoizer. What I'm going to do in the next set of material is I'm going to go through the actual implementation of said Memoizer using FutureTask instead of using the compute if absent method that comes baked into later versions of Java's concurrent hash map.